So I wanted to go over um, a couple things on the homework. Um, so 3.1, I said brief, right? And usually I put the word brief in because otherwise I get a 4-page essay. But everyone took me at their word and wrote a couple sentences, like 2 sentences for the most part. So I should have written as concisely as possible, or right in a concise manner, or something. But basically, I wanted a little bit more detail about the assumptions made in that model, right? For the most part, being, everyone talked about the, everyone hit the volume conserved. People mostly talked about entropy. What people didn't really hit was the assumptions made in the random walk model, right? Right, and the fact that we used assumed a Gaussian distribution of end-to-end distances, right? And so that's why there's a lot of check crosses, right? It's on there, and that was one of the couple questions. A couple of the early ones I went through a little more completely. So the other one I wanted to work through real fast was 3.2, right? The one about the
Poisson's ratio.
Poisson's ratio. Because there are actually a couple different ways you could do that. You get some kind of drastically different answers based on what assumptions you make, right? And the big thing is, because we're talking about Poisson's ratio, right? Poisson's ratio is only really defined in terms of a small strain approximation, right? Poisson's ratio doesn't really apply to the notion of large deformations, right? So that should kind of be a clue that we're looking for something strains small relative to 1, right? A couple of you worked out the volume change associated with a with the certain strain, and then basically solved the quadratic system and came out with an extension of about 300% or something like that, right? Which, if the question was worded slightly differently, would have been the approach I was looking for, right? I mean, that's excellent reasoning, right? So I think on a couple people who did that, I wrote a note to that effect. But we were here. I was looking for a slightly smaller, slightly simpler solution. So if we assume we have, we're going to assume that we're isotropic, right? And that we're stretching along Z. Right? And that we can replace our stretch ratio by 1 plus epsilon, right? And so we're just going to have a uniaxial compression, right? Which means that our original relationship, our current volume is the initial volume right? And then, right, this is the direction we're stretching. This is the direction that we're, the x and y direction that we're contracting along, right? And if we can just move this over here, v by v naught. Right? And since we're assuming small strains, right, this ratio is going to be approximately 1. Right? So if we put that in, and then right, our definition of Poisson's ratio is like this, right? So we can solve this in terms, we can solve this for EZ, for epsilon z, in terms of epsilon x, right? Plug that into our Poisson's ratio equation, right? So we have something that right, and then we plug that into Poisson's ratio, and we get right. So we have a rational. This cancels. We have a rational expression. This is 0.49, right, and we end up with epsilon x is approximately something like that, and then we can solve for epsilon z, and we end up with about a 3% strain, right? Which is small for elastomers, but that's very large for metals, right, or crystalline materials, right? We usually talk about metals in a 0.2% offset strain, right? When we talk about the elastic limit, right? So it's roughly an order of this is still roughly an order of magnitude more than you can stretch a crystalline material. So it involves, you know, I put this question in here mostly because it involves the notion of recognizing that Poisson's ratio is inherently defined for small strain, and that the concept kind of breaks down for larger strains. So that's the regime that we were looking for. I think all the other problems, there wasn't really anything that I saw. Again, I'll be posting these solutions either tomorrow or Friday. Right. So just administrative stuff. The final, again, is Monday the 5th, 6th, right? And it will cover up through the strengthening section with the emphasis on the dislocations, elasticity and viscoelasticity. So right. The emphasis on and then, and again, it will be 1 hour, right? Okay. So I want to hit a little bit on strengthening today. I wanted to ask, since I extended the homework, it would have been good if I brought my solutions to this location. But I think everyone is asked questions. I've got one or two people stopping by this afternoon to work through a couple things on the homework that's due Monday. If there's any questions that come up, just drop me a line, or stop by. Okay, so as far as strengthening, this is. I wish I could teach a whole course, right, just on this topic. Right, it would be. I would still be struggling to think about what topics had to be left out on this, and it doesn't necessarily seem like that big of a deal, right? The way it's presented in the reading, it seems like a pretty cut and dry topic. But I want to read a quote from a paper from Cotrell, and this was written in 2010, 2 years before he died. So he was 90 years old when he wrote this. Right? The great Sir Alan Cottrell. And he wrote this review paper that I'm going to put up on for the reading as a supplemental reading if you want to read it. It's not very technical. It's written as more of a overview style. But it says, he says, it is sometimes said that the turbulent flow of fluids is the most difficult remaining problem in classical physics. He says, not so. Work hardening is worse. He had another quote at the end. That was the opening line. The ending is that he says that he believes it is still a practical problem, but almost 70 years after the first dislocation-based theory of hardening and strengthening, the theory is still mainly at the stage of being interpretive and not at all predictive, right? It is very far from a standard theory of classical physics. And then he says it may never develop into such a theory. Work hardening is quite unique, unlike any other branch of the physical sciences. While thoroughly physical in its elements and obviously belonging to the hard science end of the inorganic world, its characteristics, huge populations of interacting individuals, competition and cooperation, organization and evolution of family groups, are more like those of biology, ecology in particular. It may be that the theory of work hardening will always look more like Darwin than Newton. Right? And in my mind, this, it takes a real genius to say something incredibly complicated in such a simple and insightful manner. So I'm going to post this. It's worthwhile for to take a glance through it, and it's focused completely on dislocation interactions. Right? It doesn't hit any of the other strengthening mechanisms. Right? It doesn't hit grain boundary strengthening. It doesn't hit solid solution strengthening or particle, dislocation particle interactions. This is simply the issue of dislocations interacting with other dislocations, right? So in the reading, there's a couple things that have caused some confusion, a little bit of confusion in the past. And so Courtney talks about geometrical dislocations, right? And other authors refer to geometrically necessary dislocations or GNDs. Right? I want to point out some important issues here. The classical picture is, imagine you have a single crystal, and you've got rows of atoms, right? And I bend this crystal now, right? If this crystal now becomes bent, I have a gradient in shear that is required to make this happen, right? At least plastically, right? Elastically, I can bend this, right? But I'm stretching a lot up here and I'm compressing a lot down here, right? In order to maintain this shape, I need arrays of dislocations to support a curvature in the lattice, right? So anytime my lattice is curved, I need dislocations present to support this curvature. And this arises naturally out of a shear gradient, right? You can imagine if I've got a grain here, right? These grains all have neighbors, right? If this is a easy grain to deform, right? And I'm at room temperature, or about at a low homologous temperature. This grain deforms plastically, right? I need to maintain, I'm not opening holes in my material, right? So I need to maintain a compatibility of my deformation. So that means I'm going to have deformation that happens in this grain, either due to the activation of pileups or for other reasons, right? And if this is also a hard grain down here, right? By hard grain, I mean one that's difficult to activate. We'll talk about that in more detail the next lecture, right? I'm going to have a gradient across this grain, which means that the orientation of my crystal or my lattice is going to have to be curved because I have a shear gradient, right? And I'm going to have a gradient in my orientation across my crystal, right? So that means I need arrays of dislocations to keep this curvature there. And those are what people classically refer to as geometrically necessary dislocations, right? So they are dislocations that support the curvature but don't have a net Burgers. If I do a Burgers circuit around these, because my lattice is curved in the same way that accounts for the Burgers vector of the individual dislocations, I don't have a net closure failure of my Burgers circuit, right? That means that there's a size dependence, right? Obviously, this is an edge dislocation, right? If I make my box and do a very small Burgers circuit, of course I have a closure failure, right? If I make it large enough, no matter what my dislocation population is there, I'm not going to have a closure of my, right? So this notion of GND has an intrinsic size dependence. Right? So it's not, this is kind of a theoretical concept. You can't look, if you take a TEM sample, you can't look at the dislocations that you see in the TEM and say, oh, that one's a GND. That one's a statistically stored dislocation. Right? You can't do it. This concept only really works when you're thinking about a large population of defects and in an average statistical sense. And you say it's the population, the portion of my total dislocation density that is required to support the curvature of my lattice that I observe. Right. The counterpoint to that is what are called statistically stored. Right. So those are all your dislocations that are not GNDs. Right. These can get broken down into mobile dislocations, right, which support plasticity. Right. Immobile dislocations, which are your obstacles. Right. GNDs are by definition immobile. And a lot of modeling efforts, we split our immobile population into what we call forest dislocations and parallel. Right? Where if this is my slip plane, parallel dislocations are immobile dislocations that lie in the plane, which is, this is basically like our pile-up dislocations, right? If there's a grain boundary here, our dislocations, we'll talk more about that. Forest dislocations thread through the plane, right? We model them at 90 degrees, but in reality, right, slip systems and FCC are tetrahedrally related, right? So they're not. It's not 90 degrees, but at some large angle, right? And obviously, if a mobile dislocation comes up to this, it's going to be stopped, right? It either has to cut through or bow around, right? So I wanted to clarify some of those concepts and ideas. And to activate slip, shoot. This PowerPoint is convenient for doing this, but not so much for going back. It's okay. So here we had our pileup. This distance of our pileup is D. Our grain diameter is capital D. We've got a Frank-Reed source smack in the middle of this grain, and over here we've got a Frank-Reed source. Right? So here you can imagine these dislocations, right? So we know we have a repulsion between dislocations of like sign. So there's a stress driving these dislocations this way, right? There's a back stress by these dislocations repelling from each other. This first dislocation is pressed up to the grain boundary. Right? This is going to give us a stress concentration at this point, right? Which gives us an elastic field that comes out into this grain, and eventually the elastic field due to the stress concentration is strong enough to activate this dislocation source here at some distance r, right? Even though we're still below the critically resolved shear stress to activate to what would be below the critically resolved shear stress to activate dislocation motion in this grain. Right? So it's all about having a stress concentration here. And this is the Cottrell theory, and it ends up that the stress to activate this, I'm not going to go through the derivation, is tau naught. This is the normal stress but for TC, this is the critically resolved shear stress. Right? And we end up with a term that's got that d to the minus 1/2 parameter in it, just like the Hall-Petch. Right? And I don't think the exact derivation is super important. Right? I mean, you want to know that the right? So I think there's only one quantitative thing that you really need to remember about this, right? What's the stress on this leading dislocation? Right? If T sub s is my resolved shear stress, right? Then my pile-up stress, if I have n dislocations, is just going to be n tau s. Right? And you can get this comes right out of the Petch-Kohler analysis. Right? So that's the only quantitative thing to remember, is that the stress at this at the tip of the pile-up is going, at the leading edge of the pile-up, is going to be proportional to the number of dislocations that you have in the loop, and that the resolved shear stress that you have available to operate sources in other grains is going to be proportional to the square root. So an interesting thing, so quite recently, a couple years ago, Professor Dunstan, is he? I want to say Imperial College. I have to go back and refresh myself for race. He's from one of those English universities. He did a statistical analysis, and he took all the Hall-Petch data that he could find over the last 100 years for every alloy, and he asked himself the question: is there enough evidence to justify the exponent being 1/2, right, or minus 1/2, right? And it turns out, if you do a standard hypothesis test on that no, there isn't. That anywhere between, there's a huge range possible, right? And so this whole theory came up with, so Hall and Petch showed that for certain steel alloys, if they plotted it on a log-log plot, they got a slope that was pretty close to 1/2. And then everyone built a whole theory around trying to get that 1/2 exponent. But in reality, it's not exactly 1/2, right? It's somewhere in there, right? And it depends on the slope depends on the alloy, right? So there's these are all models, right?
Once I heard that, what is the inverse Hall-Petch relations?
Oh, so the inverse is that once you get smaller, so if you look the Hall-Petch plots, so you have here d to the minus 1/2, right? And here you have stress. And you get points, right, that look like this. And so for different alloys, you have a line, and this is your proportionality constant, right? As you get smaller, this trend reverses. As you get really small, like single nanometer size grains, right? And the reason for that is when you're down in that regime, if you think about when you have grains that consist of tens of atoms, almost every single one of those atoms is at a grain boundary, right? So the fraction of the grain boundary, you're basically, your whole metal is a surface defect with tiny pockets of ordered atoms. And when you have that huge amount of volume of grain boundaries, it's easy to activate things like grain boundary sliding or local recrystallization or grain rotation, things that you can't do when you have a big crystal with a very thin grain boundary. Right, but that's what's meant by the inverse Hall-Petch. One of the topics I hope to get to at the end of the term is deformation in thin films and nanoscale structures, and we'll definitely talk about then. And the other topic I really want to highlight is where? Okay. And again, we're not going to spend time deriving it in class. It's done pretty well in the reading, right? But this is Taylor hardening, and this is from 1934, and if we think about the Orawan equation, right? And that's the one form of the Orawan equation, right? There's also the rate form. That basically says the amount of shear depends on the number of defects you have, the Berger's vectors, right? The size of your crystal. That basically you get right, and this is Taylor's equation, right? That your yield stress increases with the square root of the shear that you put into your system, right? And the physical derivation of this is you've got arrays of dislocations, right? And if you think about another dislocation coming in at an oblique angle to this, right? That the minimum likely distance, right? If the dislocations are separated by on average a distance L, right? The closest another dislocation is going to come without hitting into this strong interactions is going to be L by 2, right? And then you can think about the repulsive forces of one dislocation on another, right? And then think about what stress you have to overcome. You can write that force in terms of the dislocation density. Then think about what force you have to overcome, and you end up with something that looks of this form. This is one of those really useful rules of thumb to kind of keep in mind, right? Is that your work hardening is going to be proportional to the amount of shear that you put in. Right. And so I just wanted to point out the lecture, the reading, it's very dense. There's a lot of stuff packed into one chapter. It's a really important topic. It's a area of perpetual research, of ongoing research, and both from a modeling and experimental point of view, and it's not going away anytime soon. So I wanted to just pick out a couple key ideas from the lecture and the reading and say these are the important ones. And again, the emphasis is not on working through all of the derivations, right? It's thinking about it from some basic fundamental underlying physics, right? Knowing what the final form looks like and thinking about what does that equation say about what's happening in the material, rather than being able to say. So on an exam, right, I might say, explain some of the assumptions in the Taylor hardening, or what does Taylor hardening predict about this system. I won't say, derive the Taylor hardening equation, or work through Cottrell's theory and come up with the square root grain size dependence, right? That's not something that I'll ask on the exam. So, okay. Oh, shoot. I thought we'd be done early, and everything I like talking about, so.